Hey, good morning. We are going to talk more about cardiac tissue today, but just a little review of what's going on with the rest of the semester. On Monday, we're going to continue Chapter 10 on feedback. And the feedback loops is actually in the first part of Chapter 10, so try to, if you haven't done so already, try to read sections 1 through 5. And we'll spend a couple days on feedback. Homework for Chapter 8 is due today, so if you didn't hand it in yet, bring it either right now or after class. Homework on Chapter 9 is not due next Friday, which nobody will be here, but it's due 2 weeks from Friday, and that'll be the last homework assignment. And even though it's called homework assignment number 9, we'll skip Chapter 9, so it's over Chapter 10. And then just a reminder, the final exam is on Monday, December 9th, right here, 8 to 11. And also on Wednesday next week, right before Thanksgiving, hope you can make it. We will have an extra credit opportunity. We'll be playing Trivial Pursuit, Intermediate Physics for Medicine and Biology. So you can come and have a good time if you want. If you want to bring treats or whatever, it's kind of early in the morning for that, but you can do whatever you want. But it will be an opportunity to get some small amount of extra credit. Okay, so today, last class, we looked at a simple model of stimulation of cardiac tissue. It had a lot of interesting things. It talked about cardiac restitution and showed us how you can get chaotic responses. But what it didn't have in it is it didn't have space. It just talked about a single cell and how it responded to stimulation. Well, today we're going to go to the opposite extreme. Instead of talking about all this kind of complicated restitution and behavior and time, we're going to look at a really simple model of how wavefronts can propagate through cardiac tissue in space. It's called a cellular automata model. And it's basically problem number 44 in the homework is what we're going to be focused. It's not in the homework, it's in the book. It's not part of your homework assignment, but it's going to be something we're going to be wanting to talk about. So, it says, elementary models of cellular excitable media, sometimes called cellular automata, provide valuable insight into the electrical behavior of the heart. Winfrey describes one such model. A hexagonal array represents a sheet of cardiac tissue, like this. Each cell in the array can be in one of 3 states. So, the 3 states that we take is E for excited. That's what happens when you first excite the action potential. R is refractory. And Q is going to be quiescent or rest. So, we're going to reduce the entire behavior of cardiac tissue to these 3 states. And then we're going to have some simple rules that we're going to follow. So here's the rules. Rule number 1. If you start in state E, then at the next time step, you go to state R. So if you're excited, the next time step, you're refractory. Okay, rule number 2. If you're in the refractory state, then the next time step, you completely recover and you go to the quiescent state. So you're back to the resting state. And rule number 3. This is the hardest rule. If you're in the resting state, then the next time step you stay in the resting state unless one of your 6 nearest neighbors is in the excited state, in which case you flip to the excited state and the next time step. So, those are our 3 rules. Let's go over them one more time. If you're in excited, next time step you go to refractory. If you're in refractory, next time step you go to quiescent. If you're in quiescent, the next time step, you're going to go to stay in quiescent unless one of your nearest neighbors is excited, and that means like a wavefront's propagating in, and then you become excited. So what you need is some of these hexagons to be able to follow this, so I'm going to hand out some of these. Let me just take maybe 2 or 3 and hand them down your row. What I'm handing out is basically little hexagon patterns that each pattern is going to be one frame in a movie, and you're going to be able to step forward in time and go forward in movies. All right, so this is like a little game. Think of this as something that you could teach your a third grader, to play, and it's going to be amazing how much we can learn about cardiac tissue from just this little game. All right, so our first activity is I'm going to start. You have to start somewhere. If you start just with this, now my advice is put it either shade it dark or put an E in whenever you're excited. Put an R in or maybe light shading for refractory. I would just do nothing if it's quiescent because that's going to be a pretty common state. So maybe you can just say if there's nothing written in it's quiescent. So if we start in quiescent, it just sits there. So there's no pacemaker. There's no SA node in this model to get things started. It'll just sit there quietly. So we have to do something to get things started. So here at time 1, so I'll call this time 1, I'm going to make the middle node excited. Let's say you stuck an electrode there and you stimulated and you excited. What happens at time 2? So if this is time 1, then what happens at time 2? Yeah.
The 6 surrounding it will become excited and that 1 will become refractory.
Okay, good. So this, if it's refractory, if it's excited, it now becomes refractory. If it was quiescent, it stays quiescent, except for these that were adjacent to it, and these become excited. So that's time 2. What's going to happen at time 3? It's going to continue to spread. So at time 3, you're now going to become excited out here. These are all going to become refractory, and this is going to go back to quiescent. So you can kind of follow that along, and what you're going to get is you're going to get outwardly propagating wave. Now the only really interesting thing is what happens to this wave when it gets to the boundary. So literally follow the rules, propagate it out, and take a minute or two and see what happens when this thing reaches the edge of your tissue. Anybody got to the edge of the tissue yet? I know there's a lot of letters to draw.
Just all goes quiet.
Okay, it's going to all go quiet. So you're eventually going to reach the point where out at the edge is going to be an excited region. I'm not going to draw it all the way through, but behind it's a refractory region. So it goes like this, but it's all the way around. And the next step says these become quiescent and these become refractory. And then the next step, just following our rules, the whole thing becomes quiet and it goes back to quiescent and it stays quiescent forever. So the moral of the story is it does not reflect off of a boundary. It simply stops at the boundary. And that's because it's got a refractory period right behind this excited tissue and it can't go back through its own refractory period. So it can only go forward. It reaches the edge of the tissue. It just stops. So you stimulate once, you get one wave front, and then everything stops and everything's quiet again. That's a really simple case, kind of a boring case, but it's a first step. All right, let's try another case. Let's try, and you may not need to draw everything out in detail, but let's try this. Say we stimulate along this whole edge here, but also we stimulate along here. So at time 1, it looks like that. Now, what's going to happen as time goes by? So I will give you a few more minutes to try to watch what happens in this case. If you kind of see things happening, you may want to just skip a time step or two. But the real question is, as you get wave fronts coming in, what's going to happen when they meet? So take a few minutes and work on that. You might want to venture a guess on what happens when they collide. Yes?
I think they'll meet in the middle and just stop because the refractory periods can't go over each other's refractory periods.
Exactly. These two are going to be wave fronts coming in, planar wave fronts. Next step, we'll follow our rules. These all have nearest neighbors that are excited. So the next step, this is going to become all excited. This is going to become all refractory. Refractory, 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 refractory. This is going to become all quiescent. And then there's no longer a quiescent adjacent to any refractory, a quiescent cells adjacent to electric excited, so it can't go anywhere. It can't go anywhere. It's got refractory on both sides. In other words, when two wave fronts come together, they collide. Just like what we talked about with nerve action potentials. If you have wave fronts colliding, they annihilate, and you go back to nothing. Yes?
So the fact that it came from like both directions, does that affect the extent of the excited state, or no? Is there any difference between that excited that came on both fronts versus like the one front?
Not really. If you had just the top excited, you just have a wave front that would come down and propagate all the way down to the bottom. If you had just the bottom, it would be a wave front all the way to the top. So in this case, they act like two completely independent wave fronts until they meet at the center and then annihilate. Is that kind of your question?
I was thinking like more like on the cellular level, like the fact that it's receiving like two stimuli. Does that change anything?
Well, that's a good point, and this is a very simplified model. If you did this in a very detailed numerical calculation in an experiment, you might actually find that the action potential right here might be a little higher in magnitude because you got wave fronts feeding current from both sides. So you might see a little stronger action potential, but it would be a detail. It wouldn't be changing qualitatively anything too significantly. So yeah, I mean, that's a good point. In all of these, anytime you make a model this simple, you're going to have a lot of the details are just going to get covered up. Okay. Well, it may seem like this model is not all that interesting, but here comes the next step. And this is the one that I really want you to focus on. And I don't have quite as big of a setup as you all have, but this is where you want you to start. I want you to start with a line of excited cells all the way, you probably have it like this, all the way from your edge here almost the middle, and then it stops. And right behind that is going to be a line of refractory cells like this. So it's as if this wavefront was propagating up along here, but all the rest are quiescent. So I want you to start from this case and now watch what happens. And you got to do this one for several, at least 5 or 6 time steps before you can really get the gist of all of it. So start here and work your way through. I'm going to give you a good bit of time to do this one because this is the important one. Anybody viewing the video, this is the picture from the textbook of how you start this. It's dark black is excited, the light gray is refractory, and the rest is all quiescent. I once wrote a little conference proceeding extending this model a little bit. And it took me hours to make these pictures, and you just have done it in about 10 seconds. Just grab, paste.
Yeah.
Wow.
Yeah, it's a good app.
It's a good app.
Yeah.
Also, if anybody is viewing the video and wishes they had the hexagons, you can get it from the book website. If you go to the book website, there's a link where you can download a piece of paper and print it out like this. Yes?
Did you say, so you posted there's a video for this you posted online?
Well, there's the video for the class, and then there is a paper that I wrote in an online journal a long time ago, which I could get you the link for if you were interested in it, but
Okay.
it's not what I didn't give that to you guys. Maybe I should. All right. What's happening? Can anybody tell me in general terms, just from the big picture, what happens as time goes by?
Spirals.
You get spirals. You get a wave front that spirals around. Does it ever end? Don't know yet. Well, okay. I'll give you a hint. It doesn't ever end. It's just going to spiral around and around. So you're never going to go back to all quiescent. So what you should have gotten is at the next time step, well, this would have gone to quiescent. This would have gone to excited all the way around, including those two. And then these, which had been excited before, would go to refractory. And the next time step, the wavefront would go here, 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 all the way back to here. These would now be quiescent, and these would be refractory. And you can see, kind of see the spiral coming around. And it keeps going around over and over. And this is what's known as a spiral wave. This is a type of reentry. You'd find that this area where you had excitable tissue to start, you're eventually going to have a wave of excitation come up through there again. That's what the word reentry means. It re-enters. And it's going to go around, and then you'll have this area be excited again. So you just get this spiral wave. And at the edge, they just die off. So if you're standing out here way at the edge, you're just seeing it looks like wavefronts keep coming by as if there's a source of wavefronts. But there's not an SA node stimulating them. There's just these wavefronts going around and around the loop. So, I have some questions for you guys. Okay. Let's see. This was part 3. Okay, we asked, does the tissue ever go to the state of all quiescent? And the answer was no. Now, there's a special point where an excited state, a refractory state, and a quiescent state all meet. Where's that point here? Well, right there, quiescent, excitatory, and refractory. The point is right there. That point has a special name. It's called a phase singularity. And what that means is you can assign a certain phase to the action potential. This thing's oscillating, so at least once it getting in this spiral, it's oscillating. So you could say, well, the first phase is the excitatory phase, then the refractory, and then the quiescent. And the only place where those all meet is right here. There's no other spot. Sometimes 2 of them meet, but there's no other spot where all 3 meet. And the phase singularities are kind of like the North Pole. You can talk about what's east and what's west anywhere on the surface of the Earth, and it makes lots of sense, except when you get to the North Pole, and then you can't really talk about what's east and west because it's all kind of a singularity. They all meet there. Well, here, you can talk about an excited part of the tissue, you can kind of talk about refractory, but right at that point, you don't know whether the tissue's excited or refractory. You don't know if the transmembrane potential is going up or coming down. It's or it's all just sort of quiescent. So at the heart of any spiral wave in cardiac tissue, you'll find one of these phase singularities, and it's good to get used to trying to spot them. In a real cardiac simulation, you'd have a wavefront coming around like this, and this would be the excited edge, and this would be the refractory edge. So this is all the plateau phase of the action potential. And they come here, and it's clear that the excited part's propagating out like this. But right here, somewhere, the refractory comes and bends around. If you think of this as a certain transmembrane potential, so maybe halfway up. So if it's at rest at minus 70, peak is, say, 20. This might be minus 20 millivolts. Minus 20 millivolts is right in the front of the excitatory region. It's kind of halfway through the refractory. Right here, is it going up or going down? Can't tell. That's the phase singularity right there. So, we are able to apply these phase singularities. Now, another question. And how many are there? Well, there's only one in this particular example. Another question. Do they move? Does the phase singularity move from time to time? So look at your results and tell me whether the phase singularity moves. You think it does?
It would get to the point where they all meet, moves with the wave.
Well, how many think that it moves? How many thinks it doesn't move? Okay, we've got the majority are refusing to answer, but we have a slight majority. When I do this, I get that in this model, the phase singularity doesn't move, because the next time step, you're going to have let's see what happens the next time step. This is going to become excitatory, as well as these, but they don't matter. This is going to become refractory, and this one's going to become quiescent, and they still meet at that spot. The next time step, this will become excitatory, it will propagate into there, this will become refractory, this will become quiescent. And you should find in this model that the phase singularity is stationary, and the whole thing propagates around it. So you have to really do this carefully and make sure that sometimes it's easy to miss one of these down here. The excited one swings around, but in this case, the phase singularity doesn't move. Now, in real cardiac tissue, you can sometimes see the phase singularity moving around. It's what's called meanders, is the term that's used in the field. You can find that in real cardiac tissue, the center of this phase singularity moves around. Sometimes it moves around in beautiful little flower patterns that look like this. Looks like a spirograph game. But in our simple model, it doesn't. You're going to find when you look at the practice exams, there is a case of a slightly more complicated model. And you can, even if you make it slightly more complicated, you can get the phase singularity moving around. Okay, one final question about this. What is the period of the spiral wave? In other words, if you were standing out here at the edge and you see these wave fronts come by, how often do they arrive? What's the period of the spiral wave? Anybody see that from their results? Yeah.
6 time periods. Not sure what to call it. 6 time constants.
In some ways, you're correct, because if something has a period of 10, then it also has a period of 20. But it's not the shortest period. You would actually see it come by more often. It's every 3, because it starts off, say, excited here. Here's at the phase singularity. Excited, quiescent, refractory. So spiral wave going around. The next point is going to be E here, R here, and quiescent here. And the next point, it's going to be E here, quiescent, refractory, and then the next time around you're going to start right where you started. So it's sometimes there's a little slow. The transients in the spiral wave building up is you have to kind of ignore. But once it gets up to where it's going around and around, it's got a period of 3 in this example. So you can see that when you have a spiral wave, it sort of sets its own period, as opposed to being set by a SA node. And it's a fairly fast period, which is why spiral waves are what underlie ventricular tachycardias, that arrhythmia that we saw when we were looking at the EKG that usually had a very fast rhythm that was kind of sinusoidal. It's because you have the cardiac arrhythmia. Now, one last question. Does the spiral wave in this case propagate clockwise or counterclockwise? Yeah, clockwise. This one's going clockwise. So it's going around here, then to here, here. So it's going around clockwise around the phase singularity. If we started out with our different initial conditions, so it looked like this, refractory, 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 and you had your phase singularity here, then it would start going around like that, and it'd be counterclockwise. So there's 2 types of phase singularities. They're exactly the same, except they have different polarities. They have different clockwise versus counterclockwise. So this is a simple model. 3rd graders could play it, but it has a lot of information on the way cardiac tissue behaves. Okay, so we're going to continue on with this, and we're going to go on to problem number 45, which is a continuation. Okay, problem 45. In cellular exciting medium, described in problem 44, what happens if you apply an electrical stimulus? The stimulus is described by a 4th rule. So the 4th rule is at the time you apply your second stimulus, you're going to apply a stimulus, then some later time you're going to apply a second stimulus. And that stimulus changes one point in the center to E, regardless of what its previous state was. So everything else is the same, except we're going to say, bang, give a stimulus at some time, and that center point where your stimulus electrode is going to change to E. All right. So what we're going to do now is this. You're going to start with at the bottom of your array. So this would be all the way at the bottom of yours, but mine doesn't extend quite to the bottom. You're going to have all E's and nothing else. Everything else is quiescent. That's going to be time 1. And then you're going to start walking through just like we did before. But at time, let's see, it tells you, let's try to apply the stimulus at time 4. If you apply the stimulus at time 4, what happens? So you go through and you're going to go 1, 2, 3, 4, write down everything for time 4. And then as soon as time 4 is over, you take the very middle cell in your frame and you make that excitatory, and then you let it propagate again along there. So try that and see what you get. Does anybody need more paper? Okay. Here, I'll just, there's a couple of those. I know that I don't have a different supply, but got a few more. Yeah, you may want to actually jump over the first 3 time steps or something and just jump up to the 4th one because it's going to be obvious what it does until it gets to the stimulus at time step number 4, and that's where things aren't quite so obvious.
We're going to stimulate that in the center?
Yes, only one node in the center, not the whole row, one node in the center. That's where your electrode is. I'll put it this way. Right here at the center is going to be your electrode node where your second stimulus gets applied. You can say that this was your first stimulus all the way along the bottom. It's going to come up, up, up. Remember, yours is all the way at the bottom of your thing. And then right at the center, right after time 4, right at the center, you're going to say stimulus applied there. And that's going to be the only change. Okay, while you guys are working on that, people looking at the video, this is actually the answers for the first problem. Okay.
So the first box that you drew with the excited on the box, that defines time 1 or time 0?
It's time 1.
Time 1.
And it's really at the very bottom of your big hexagon array. Yeah, so I really need to have a bigger array to make this clear. Let's see. How many of them are there? There it is. 1, 2. Okay. I'll let you guys play the game a little more. right, well, this is what I get at time 4, right before the stimulus is applied. And then you apply the stimulus, and this cell becomes E. And then what happens? Well, there's two ways to do it. You could just play the game, and what you find is you get this wavefront that keeps going up. It's got a little bump in it in the middle. But another way to look at it is, are there any phase singularities? Because if you're going to get reentry, there'd have to be a phase singularity. And there aren't, because this E doesn't have any refractory ones by it. There wasn't any phase singularities to begin with, and adding that in there didn't cause a phase singularity. So the bottom line is, in this case, you had a wavefront that was propagating up, and you stimulated too early. And all you really did was create another wavefront that sort of immediately collides with this one and becomes a combined wavefront that just propagates upward. So the bottom line is you stimulated too early. So if we stimulate too early, what we should do is stimulate a little bit later. So let's start again with the bottom row is excited. But let's now, instead of stimulating at time 4, let's stimulate at time 8. Okay, so try that one. And again, you may want to just do the first 7 time steps really all together. So while you're working on it, I'll begin to work on it here. This is time 1 right there. So we're going to stimulate time 8. So it looks like this right before you stimulate. And then you stimulate E. What's going to happen? Well, we can just kind of say it in words without actually doing it. This thing is going to start a wavefront propagating out as a circular wave. This is kind of right at the edge. It's going to go up to the top and die away. So you get your first wavefront, and then after it passed by, you stimulate a second wavefront. Both of them will propagate out to the edge, die, and then you go back to completely quiescent. So the bottom line is, in this case, you stimulated too late to get anything really interesting. So 4 was too early, 8 was too late. So let's try this. Let us start with this wavefront here, and let's stimulate at time 6. So I'm going to let you do this. This is the most interesting one. So you stimulate at time equals 6. You stimulate. So if I were you, I would just jump up and immediately go to 2, 3, 4, 5. 6, get your wavefront going across, and then add in your stimulus. And the stimulus says that no matter what the state of this is, we're going to change it to E, and then watch what happens. Got a few more sheets of the paper here if anybody needs them. Yep. Okay. Yeah, you don't use this old style stuff.
So if it's too late, it'll stop propagating.
If it's too late, you'll get 2 wavefronts stimulated. 2 stimuli gives you 2 wavefronts, but it won't continue. They'll go to the edge, die, and then you'll go back to quiescent. If it's too early, you'll basically get 1 wavefront, which will merge together and no reentry. other sheet. There you go. Well, at time 6, I had it looking like this right before I stimulate. So here it is, the wavefront's coming across, and then as soon as I get to this, I say stimulate, time 6. That means under this one, I change it to E no matter what it was before. Now, what happens? First question, are there any phase singularities? There's 2 phase singularities, right here and right here. 2 phase singularities. So at the next time step, these 2 have E next to them. They go to E. These were all R. All the E's go to R. And all the R's go back to quiescent, including this one. No.
You already changed.
No, that one I already changed. These go. And now you're like this. You have a new wavefront propagating back the other direction. The next time step, this is going to begin to go out here. That will go back to quiescent. And then these 2 will be able to converge back in here and propagate, and you're getting, what is it going to look like? It's going to look like 2 spiral waves. 2 spiral waves which keep going around and around, crash into each other, go back down, split up, crash into each other. So this is really kind of cool because once they crash into each other, they create these closed wavefronts. So if you're standing out near the edge, you don't just see wavefronts coming by, you see closed wavefronts coming by as if there's a pacemaker right in the center. They keep coming in over and over, really every 3 time periods. But if you look close what's happening at the very inside, you see that it's actually what's called a figure of 8 reentry. It goes around and around and comes back together, giving you the figure of 8. This experiment has been done in cardiac tissue. A guy named Ray Idecker at Duke did the experiment where he basically set up a line of electrodes down here, gave a first stimulus, a point electrode right here, gave a second stimulus, and you can get these phase singularities. Then the question is, when do you get them? Well, it turns out that if you did this analysis carefully, you'd find that at time 6 and at time 7, you're going to get phase singularities. Any other time, you don't get them. So this leads what's sometimes called the vulnerable period. As you launch wavefronts across, if you stimulate at just the right time, you can get reentry started up. You start up a ventricular tachycardia, which doesn't decay into fibrillation in this model, but in the real heart could easily decay into fibrillation. So you have to stimulate at just the right time. And the right time is when there's a refractory period, there's refractory tissue right or close to where you're stimulating. Otherwise, you can't get a phase singularity. Because if you don't, you're going to get an E here, and you're always going to have some quiescent tissue, but you've got to have the refractory tissue around. And that only happens when this wavefront comes and gets you a refractory period right near where you're stimulating. Then you can get phase singularities. So there's a couple lessons to learn from this. One lesson is that if you want to start one of these, you stimulate near the end of the refractory period. And that means, if we go back to the electrocardiogram, that means if you want to stimulate reentry, what you'd do is you'd stimulate near the end of the T wave. The T wave is the ventricle repolarizing. That's the vulnerable period. If you stimulate right in there, you can start up one of these tachycardias. Or if you stimulate too early or too late, you generally don't. So remember when we were looking at the electrocardiogram, we saw those premature ventricular contractions that would sometimes appear? That was one of the electrocardiograms you're supposed to know. If you had a PQRST and then a little quiet time and then you had this premature ventricular tachycardia, that's not going to be a big problem. It's too late. But if this thing moves back, so it stimulates a premature tachycardia right near the end of the T wave, it could easily set up one of these cardiac arrhythmias. So it's a very narrow window where stimulating is dangerous. And this leads to another story about a electrophysiologist, and now for some reason I'm blanking on his name. Drat, I should have looked it up before class. But he was a British physiologist back around the time of World War II. And he was known for sometimes doing experiments on himself. So he put electrodes on his chest. Maybe I've told you this story, I don't remember. He put his electrodes and he'd stimulate his own heart. And then they came in one day and they found him lying dead on the floor. He had stimulated at just the wrong time. And you stimulate just the wrong time, you throw your heart into tachycardia, which decays into fibrillation. There's nobody to defibrillate him, and you die. So you got to be careful. First of all, be careful of self-experimentation. And second of all, it just brings out the point that the timing is really crucial for when you stimulate. And that's why it's so hard to defibrillate. One reason defibrillation is so hard is because if you just turn the entire heart to excitable, you defibrillate, because now the entire heart's excitable, there's no phase singularities, everything's okay. But if you have any wave fronts through the heart and you change almost the whole heart to excitable, but you missed an area right over here, so you change this whole side to excitable, but you missed this area here where there's a wave front propagating up. Well, now you'd have all excitable, and right around here somewhere you'd have a phase singularity, and it'd start up a new reentry, and you'd end up failing in your defibrillation. So one of the things that I've studied a lot in my research is why defibrillation shocks fail, and it's in part because you can maybe reset most of the heart, but set up a situation where you can restart the reentry after the shock. So there's a lot of interesting things going on with these phase singularities. The amazing thing to me is you can learn so much about them just by playing this silly little game with hexagons, but you can. So that's a little bit about cardiac electrophysiology in a nutshell, and how it behaves. It's really the homework problems in chapter 10. These ones you weren't assigned, but are worth maybe looking at. In fact, you'll find on one of the practice exams you have some hexagons to play with. Any questions on that? Yeah?
Does how the SA node keeps like a rhythm, or is it totally different?
No, the SA node does not work by reentry. The SA node is a fifth rule. The SA node says that everywhere in your heart obeys the rules we were saying, except for this special node. And this special node says if you go to quiescent, the next time step you go to excited, because it's got just in its natural behavior is different than the rest of the heart, and its resting potential is not stable. So no, there's not a tiny spiral wave or figure of 8 reentry going on in the SA node. It is a different type of a tissue. So it's as if we're stimulating over and over and over at the center. Other questions about the model? Another way you can start up a phase singularity is you can start the wavefront propagating up from the bottom, and then at some time you can stimulate along this edge, and you can get a wavefront that looks like it's propagating across this way, but they will, they'll meet down here somewhere, and it's called cross field stimulation. It's a way experimentally you often start up phase singularities. And the other cool thing about this is the location of these phase singularities in a real heart, because in a real heart this refractory period is not just 1 millisecond, it's a long time. In a real heart you can just basically create these phase singularities wherever you want them by waning different times. As long as your refractory period is kind of near here, you can move the phase singularities around, and you can even move them around in this direction by how strong you stimulate, and you can play with it. And one other thing to note is there were two phase singularities, but they were started in opposite-handedness. One was clockwise, one was counterclockwise. You can never just do this and get two clockwise phase singularities. They always kind of get produced in pairs, clockwise and counterclockwise. So you can sometimes get one, but that's because you're near the edge, and if you had done a bigger sheet of tissue, there would have been another one going the other direction way over here. All right. On Monday, we're going to start talking about feedback, and just sort of get away from the heart now and talk about general feedback loops in the body. We'll spend Monday, and then we'll spend a week from Monday talking about feedback, and then it'll just be reviewing. I gave you the practice exams. We'll be going over them Wednesday and Friday of that week, and we're done. Okay, remember, if you didn't hand in your homework, hand it in right now. I will see you on Monday.